Yeah, thank you for giving the opportunity here to talk about WoAT urban canopies. I will really focus on the lowest part. It's similar in scale to what Ned did for the vegetation canopies. I start with some general thoughts about what is the need for this research. Let me see, yes. It is clear that this is the place where we live. I mean, more than half of the world's population resides in cities, and they don't live somewhere up or underground. So the urban canopy layer has a huge relevance for our everyday lives, for the health, safety, economy of the world population. And in particular, the dispersion of pollutants has gained a lot of attention in this context. But it's not only the pollutants. If we think about why we study urban turbulence, in particular in the canopy, it is that we have to also work with weather forecasting, extreme events, winds, downbursts need to be forecast. It is not only the pollutants in the long term, the air pollutants, it's also release of dangerous materials, dispersion, but also more recently, the dispersion of greenhouse gases if we want to measure greenhouse gas emissions from cities. And less, but still quite relevant, is the aspect of renewable energies. I'm not talking about bringing wind turbines into the city. I'm more talking about the energy of buildings. So Marco Giametto, for example, showed that trees in the city, they lower the wind and pressure fluctuations, and that calculates or that translates to a significant energy saving as well. So if we want to move towards energy conservative or energy reducing cities, we also need to think about wind. A few buildings at the a few pictures at the beginning to illustrate some of the particular effects we see in cities. Wonderful picture of flow over buildings. Unlike vegetations, buildings are not permeable. They are not moving in the wind, and they are very sharp edged. That means the pressure perturbations that Ned also talked about in the averaging, they are even much larger, and that changes the airflow and, of course, the turbulence, in particular in the wakes. But that's not only the only complication. If we contrast that also to vegetation canopies, the volume occupied by buildings is substantial. If you're here in downtown Innsbruck, probably more than 50% of the space is occupied by buildings. So indoor air that is decoupled from the outdoor, and also the outdoor air volume as we go down into a canopy is decreasing, and we have to account for that in equations. Another specific aspect is the location of heat. While in let's say flat terrain, the heat sources are uniform at the surface. In a forest canopy, one can also argue it is the canopy top, but in a city this is greatly human influenced. I mean, there are huge emissions from chimneys, from venting systems that are controlled in their timing and controlled in their location by human decisions. And we, of course, can also alter this. And finally, I will not talk a lot about this, but it's an interesting side aspect is, in particular, if we deep in the street canyons where emissions occur, there are also moving objects. And so the airflow is affected by those moving objects, and there has been a couple of studies looking at traffic-induced turbulence. That is something that is sometimes relevant. Now, I will focus not on all turbulent motion in the entire boundary layer. In this overview presentation, I will focus on some of the progress made in the area near the urban canopy, and you see the separation. This is mostly the lowest 10%, so essentially what is the surface layer? The surface layer over city, yeah, you can see that here the surface layer is separated as over other rough surfaces into an inertial sublayer where we can essentially assume some, if we have horizontally homogeneous roughness, some one-dimensionality and a roughness sublayer below. So that's inertial sublayer and roughness sublayer. What Matthias Rotach pointed out as well is that if the roughness elements become really tall, like in a downtown environment, the roughness sublayer might actually take up the lowest 10% of the entire boundary layer, and we have no longer the possibility to use inertial sublayer conditions. So some of the dispersion models will fail, clearly. Now, within the roughness sublayer, we also have the urban canopy layer, usually defined as the area that's from the top of the buildings down, and that's where most of us live. Now, very quickly, the early work on urban turbulence mostly focused on isolated buildings, came from an engineering perspective, and I can, without going too much into the details, say that airflow around isolated buildings is fairly well understood, even though it looks chaotic at first. There has been lots of wind tunnel studies and also numerical work on some of the nice features, such as the horseshoe vortex that develops here around an obstacle can also be seen here in Tim Oak's textbook. Instead of focusing on those isolated buildings, also a large body of work was looking at the spaces in between in cities. And if we can say there are buildings, there's also space between buildings. And this space between buildings is usually occupied in our cultural, or in most of the cultures, by streets where people move or drive and where emissions occur. And so another approach is to look at street canyons as an element that's repeating over cities. And studies try to relate few length scales, for example, the height of the buildings to the width of the canyon, usually studying infinite long canyons to make things easy in relation to wind and stabilities, and how this affects, of course, the venting of pollutants. One early study that I thought is an interesting approach from an experimental perspective was done in the 1980s in Chicago, where they released small balloons, and with a camera tracked those balloons, and you can see those trajectories of those balloons. They circle around and they are trapped in this canyon, and we can of course argue that also happens to air pollutants. And the wind here is, of course, on top from right to left, so that creates this, what I show here, this canyon vortex. That changes with the direction of the air approaching flow. I just show some more recent simulations that Marco Geometra has done for part of Basel with large eddy simulations. And although this is a complex canopy, you see some of those features. So those are trajectories, and you see some of those looping movements here, and also here are found over and over again. So there was research on looking how we can parameterize this in models. How long do they stay in a canyon, which of course relates to the situation. But summarizing this work on individual elements, is a city, and the last picture has shown, is more than the sum of its buildings or canyons. And we really need to look at the urban scale flow interactions. We have to deal with a realistic geometry, which is far more complex than in a forest. We cannot approach one-dimensional approaches, many scales and degrees of freedom. It's challenging to study because we cannot measure everywhere, every place, no universality. How can we classify those surfaces? So what the field has done, going back again, of course, to simple surfaces, and first study idealized geometries, cubical building arrays, with limited degrees of freedom, and try to figure out if we can find universal scalings in terms of spacing, density of those arrays. Of course, the question that the community has driven now for a long time is as well, how transferable is that from a practical perspective back there? But I don't think it's a bad idea to make the system simpler and to try to identify the most important scalings. That leads me to more a practical part of research that was done in the last, I would say 50 years, not 100 years, looking at urban dispersion. I mean, from a health aspect perspective, from an air pollution perspective, also for planning response actions or assessing risks, emissions from power plants or accidental releases. A large body of research simply needs to know where does a cloud of something that has been released go and how quickly it disperses, without actually knowing too much about the underlying. It's good if we know something about the underlying physics, but it's a very practical engineering work. And some early approaches used, again, idealized obstacle arrays. Those are some videos I was able to digitize from work that was done in the UK in the 1980s, where we have different arrays. Now I need to see whether I can change the situation. So in wind tunnel simulations, where you release smoke and then you implement different different roughness elements of different densities. You see that now here, that how this affects the flow. First of all, the vertical mixing, the vertical transfer is much larger, but also how is this affecting the lateral transfer? And then, as you can imagine, in a wind tunnel, I don't show the entire video, you will essentially increase the density more and more, and from those visual and measurement perspectives derive some general relationships. So one thing that was found in this work is if the elements are too far apart, there is no really significant lateral interaction. Essentially, the buildings will affect the flow, but it will not have an interaction. At the opposite, if you put the buildings too close together, there is no airspace where dispersion can happen, and essentially everything happens above roof level. So in between somewhere, there is the highest lateral spread, and that has some practical implications, because that's also relevant how we design cities, because we want to promote dispersion. Dilution is not the solution to air pollution, but it is one way of managing it. Of course, we have to tackle things at the emission scale. This work led to the recognition that there are different flow regimes. So flow regimes that are essentially can be described by individual roughness elements and the flow around a building, where the flow is readjusted to the conditions upstream before the next element is encountered. That would be isolated roughness flow. It's not really relevant for cities because usually buildings are closer, but in some cases that's the case. Then we have wake interference flow, where one wake of the building is really impacting the next building, which causes a lot of mixing and a lot of lateral spread. And then we have a situation, if the buildings are even closer, where the space in between is enclosed and increasingly decoupled from above. And you can imagine that from an air pollution perspective, that's of course not a situation that is an advantage, while this is something we would like to favor. But that's not the only thing. I mean, the views suggest it's only the density, but it also depends on the alignment. So studies have been done with staggered arrays versus aligned arrays. And then also, if you change the height of the buildings to being more random, that has great influences. So that essentially should be, first of all, an indication that if we go from here to here, the vertical and lateral dispersion is increased, but also that with those simple arrays, we cannot just guide society in terms of how to build necessarily cities. Reality check. How can we see whether those dispersion aspects are fulfilled? One option is to use tracer studies, because that's the more realistic compared to doing measurements of the three-dimensional flow everywhere. And early on, such urban tracer studies have been done, traceable back to the 1950s even. Not much is known about those, because some of this data is still classified or not at least released, because it was linked to the question, how do biological agents disperse in cities, and how this can be actually also used for warfare. Same in St. Louis. Interesting, they used also some ugly substances at the time released in cities, for example, cadmium particles, which we no longer would do today to look at dispersion in cities. Those experiments increased in complexity. There were some high-level releases from Sven Erik Grüning's group at, let's say, 150 meters above a city, and then progressively moved into the canopy layer. Also, what's interesting, some coupling outdoor and indoor space, because again, from a practical perspective, that is relevant, or even tracking human exposure or essential dispersion in subways. The other option we have more recently is, of course, to use building result models to look at those effects. That's studied on by Scott Zaleski from Oklahoma University, and he modeled here a dispersion of a point source in a residential area and looked at the effect, for example, of trees. So that's essentially mixing what we heard before, canopies with the bluff bodies, and how this affects dispersion. Now, nevertheless, in many applications, that are more of fundamental nature. So that means more in numerical weather prediction, also more recent in climate modeling. We need to even reduce the canopies to a more simple approach and make it a one-dimensional approach, essentially only looking how things change from the surface as we go up in the atmosphere. Only the vertical exchange needs to be considered in a simple way. Interestingly, that has been done, and that's more than 100 years ago. Matthias Roth points to this in his overview paper, that measurements on Eiffel Tower in Paris have been done in the 1910s and 20s, and they found that the transfer of heat by looking just at profiles was more efficient in the city compared to outside the city. So in a cartoon, what we want to do is we want to, in some applications, go away from a true three-dimensional field of turbulence into something that is only one-dimensional, where things change by layers. So essentially, the spatial averaging operator you already introduced, so that we have changing wind or changing turbulence properties with height. I mean, in some other applications, we even don't care about the detailed vertical turbulence, and we just need to look at the exchange. But I will mostly focus on this case B here, because that's interesting to this community. Some models have been developed to, of course, accommodate urban forecast air pollution, but also heat exchanges. And they can be classified in bulk approaches where we don't care about the vertical situation, single layer models where we have a canopy space and we have some kind of above roof, for example, temperature, and that's the most interesting for the work we do here, multi-layer approaches where we have spatially averaged properties with height in a canopy. I just list some of those here. For example, one important model is the BEP model, as probably the first multi-layer urban canopy model that now recently also included vegetation effects in the community. And because I'm an observationalist, I mostly work with measurement data, I thought I will show some pictures as well from early approaches. That's something Tim Oak gave me. It's funny how they climbed the tower. That's, by the way, Doe Stein from the University of British Columbia at the time, being a student. And the interesting systems as well you see here is there was a bone ratio apparatus mounted on this urban tower here in this area of Vancouver in Canada, where they tried to look at differences of temperature and humidity to look at the energy balance. And it never worked nicely. It was actually, the differences were too small because of the large scale turbulent motions. Also interesting, the first work not using sonic anemometry, but 3D propeller anemometers on top. This famous tower is the work of Matthias Roth in Zurich, which was established on this pedestrian bridge here. And Matthias, in a very intelligent way, had only, I think, 2 sonics available and switched them to different locations, and could show that Reynolds stress is height dependent in this vertical part, and the assumption of a constant flux layer is violated. But he could also show that local scaling that was proposed in other contexts can be applied to cities. So here is an example of a similarity relationship, sigma W over U star, and not using the U star locally, but the U star from the top, and it doesn't match as well. But if you think about that, the U star changes locally as you go down to the canopy, those are the measurements, you apply that, it gets definitely better. And you come closer to this. So that was essentially an opening to look at local scaling approaches that could work. Also similar, at the same time in Vancouver, Canada, other Swiss colleague Matthias Roth and Tim Oak, they did spectral measurements of turbulence on the tower, and they find that dissipation of turbulent kinetic energy is relatively small looking at the inertial subrange. And what's interesting, at the time, they speculated that perhaps this is an increase in the transport term that Ned already mentioned, and I will show that actually that is most likely the case. Research also went on tall towers. This is a nearly 100-meter tower in the city of Basel, where Christian Feigenwinter has equipped 3 levels of sonic anemometry and essentially tried to use local scaling. And local scaling at the different heights here for sigma W or for sigma theta seems to get relations, but it doesn't fit. The lines here are the surface layer values. It does not fit the surface layer values. So even if we are in the inertial sublayer, we have problems. And he was, of course, also inspired by the work done in plant canopies and applied those conditional sampling techniques and could show that large coherent structures affect the exchange. In the case of this study, about 70% of the momentum exchange and 90% of the heat exchange at the lowest level was attributable to those coherent structures. The influence decreased. Up here, it was only about 70 and 50% of the, or vice versa, sorry, 50% momentum, 70%, yeah. We then followed up in 2002 with the bubble campaign, also in the city of Basel, that was led by Matthias, and where I did my PhD, and we had the luxury to have 3 towers at the same time. So in different densities, different configurations. And at those 3 towers also have measurements over 1 year. And it was always mentioned yesterday, having long-term data sets, not just a couple of days, but at least a year long, is very valuable. And I can definitely say that, because you can really find more exotic situations. You can derive relations. Again, here similarity relations. This is for sigma W over U star as one example. It's hard to see, but the thin line here is the prediction, but you can see it changes. And in some of the levels, for example, just above, below rooftop, this is completely different from anything near any kind of prediction. So the local escape variances, they greatly depend on height. And now we could say, okay, let's give up, or let's hand over the data to Ivana for looking at new approaches. But also, what was nice in the Basel data set is that we had 3 towers. And if we put together the 3 towers, it's not just random that they fluctuate once higher and lower. For example, if you look at the neutral limits of sigma W over U star, they change similarly at the 3 towers. I tried to explain this with the turbulent kinetic energy budget at the time. If we assume local scaling, we essentially assume a local closure, that the mechanical production that includes here the wake production, by the way, and the thermal production is simply balanced by local dissipation. And if we do this, it doesn't look bad, but essentially we don't balance this. And if we add the non-local closure terms, we can measure the triple correlations. That's also a need for long-term data to have to essentially get rid of the noise. You can have a pressure transport, and that's similar to plant canopies. So essentially, the pressure is exported, or the turbulent kinetic, not the pressure, the turbulent kinetic energy is transported up and down in the canopy from a region where there's most of the production. Pressure transport we cannot measure, but we used it as a residual, and it indicates that it is essentially here a loss, and it is a wind up and down, which is also consistent with some of the large eddy simulations. So local scaling, I was arguing, is failing because we don't account for those additional terms. So the solution would be to go for higher order closures that account for those. Now, in the meantime, we have lots of studies. This is a family portrait of flow over urban canopies. So here that would be the top of the canopy. So it's scaled by the mean height of the canopy. And you see that all those studies to some extent converge. So this would be the wind profile, again, an inflection point similar to the forest canopies. Here, the momentum flux. Interestingly, most studies show some kind of peak near the rooftop. This would be the correlation coefficient. So the momentum flux increasingly decorrelates as we go down, also similar to would separate the roughness sublayer into an area that's deep in the canopy, so essentially between the surface and about 2/3 of the height, where the flow is mostly dominated by the structures that penetrate into canopy. Suites dominate. We have a shear layer where there's intense shear between about the upper part of the canopy and at least 1.5 times above the buildings, where we have the characteristic that the neutral limits of the velocity variances are significantly lower than predicted by local scaling. That means some of this is essentially exported and cannot be explained by the local scaling. We also have an inflection point, and we have a layer. I'm not sure if we should call it blending layer because there are other definitions, but where it goes into the surface layer and we are dominating, the flow is dominated by ejections. So in summary, what were the most important contributions? The first part of my talk showed that the community has used idealized geometries, well understood cubical buildings, infinite canyons, surfaces of aligned and staggered arrays. And from this, a lot could be learned. But the question remains how transferable that is. Practical needs on the other side, in the second part of my talk, showed that we need to have information on the lateral and also vertical dispersion in urban canopies for practical reasons. Difficult to derive universal scalings in relation to morphometry. It's partially possible with the unified geometries, but is that transferable to the real world? And finally, in the last part, integral and one-dimensional horizontally averaged statistics, they show converging turbulence behavior. We are seeing similarities across cities, across the globe. So that's what I call the urban family, as opposed to the plant canopy picture that Mike Ropak has compiled. But also, I want to make the point again, known local processes dominate the transport of roughness sublayer, and that's quite similar to the vegetation canopy, although we don't have the mixing layer analogy, I should say. We don't have that in at least not all the cases. Last decades have seen an increasing effort put into more sophisticated 1D models, numerical weather predictions. We are now able to model cities, and we need information on pollution concentrations, on temperature at the level of cities. What are the open questions? In cities, we also have dispersive stresses and fluxes, and I have said little about those. They contribute possibly quite even more compared to plant canopies, and some of the few studies that looked at it using either LES or direct numerical simulations show they are important. Volume averaging, that's actually something that is quite crucial. As I mentioned before, that the fraction of buildings is increasing here in this case from one of the towers in Basel up to 50%. So how do you actually calculate vertical gradients if your volume is changing? There's a nice work by Manuel Schmid looking at those averaging procedures and what it means for our budget equations. Pressure transport, as I've shown, is possibly more relevant even compared to vegetation canopies. But how can we include that in scaling? How can we even do measurements of pressure transport? Thermal plume effects, as I showed on the image, where we have locations where heat is increased, and scale interactions are relevant. Just 3 slides on some of the next steps. From a practical perspective, modeling perspective first, we have now large eddy simulations that can run not in real time, but they can run entire areas. And they are still slow, so they cannot be used for forecasting. But what some of the groups have done have moved them to GPU, and what I show here, also you can actually use large eddy simulations and apply machine learning approaches. For example, in Freiburg, we have an interesting project where Dirk Schindler and together with Marco Geometra, they look at different neighborhoods. They model with LES, and they do a training, and then they apply it to a test area that has not been trained before. So that's over here with machine learning, and then compare it to large eddy simulations. And that seems to be quite, from a practical perspective, efficient, and it has computing advantages that it's 4 orders of magnitude faster. So you can use that maybe in the future for dispersion modeling. Now, from an experimental perspective, and you asked me to say something about the ERC, we currently have an ERC running that looks at interactions of urban climatology across scales all the way to the globe. And we need really to do observations as well across scales. So we just finished a campaign in Berlin This is the city of Berlin, and this is a radius of 20 kilometers. And we combined remote sensing observations, LiDAR, ceilometers, with essential local scale situations in a way that we have first a main transect along the main wind direction, so we can look how things change over the city. We also are interested how it actually behaves laterally to the boundary layer and what's the intra-urban variability in a grid-spaced approach. To complement this boundary layer observations, I just wanted to show what you can see. But if you take here for one day boundary layer observations in the upwind area, the wind comes from the west here at the fringe of the city, and you contrast that to the city center, you see the boundary layer is higher over the city because there's more heat going in, there's more vertical mixing. Interestingly, if you go to the rural area downwind, that's the yellow one, it stays high. So we have urban plume effects that even go beyond the city. So we cannot actually just study the city. We need to study the entire region in a model. But what I wanted to show is also to scale up individual tower measurements. Those are tower locations in Berlin that were operated to path average scintillometer. Good. With this, I'd like to thank you for the invitation. I acknowledge the support from a number of colleagues that either contributed photos or research to this, and of course also the research of some of which has been funded by the agencies below. Thank you.